Hello, everyone. Let me thank the organizers for inviting me for to the contribution talk, and thank to Ali Reza and for the chair of these sessions. And actually, you had very exciting topics and talks from the early mornings today. It's just so, as you can see on the screen, I'm going to talk about the kinematics of stars and gas in brightest group galaxies, the project that we started recently, and we try to understand the role of group dynamics in the galaxy evolutions, and try to starting with the brightest group galaxies, which is located at the center of galaxy groups and clusters. So in this studies, we're using the observational data from SAMI and gamma surveys, and we have lots of collaborators from these two surveys, two big surveys, and also some of the staff working in the custody. So okay, let me to have a brief introductions about the key parameters that we have. Okay, the key parameters we have is the galaxy groups and clusters. The galaxies are not randomly distributed, and they tend to aggregate together into a small collection of galaxies known as galaxy groups and clusters, consisting of a few up to 1,000 number of galaxies and members. So the groups are smaller and which have less than 50 bright galaxies and have a low velocity dispersion, which lead to have a low halo mass around the logarithmic scale of 10 power 13 to 10 power 14 in solar mass. That and you can see in the pictures the typical example of the galaxy groups, the Higgs compact galaxy groups. That's including some of the big galaxies at the center, and lots of satellites around there. So the cluster is larger, and which have a population around 50 to 1,000 galaxies, bright galaxies, and specifically have a higher velocity dispersion, which lead to have a higher halo mass. It's over 10 to 14 in solar mass. So so the next things is the galaxy interaction. The slide is slowly load. I don't know why, but the galaxy interactions. So we know that the low velocity dispersion of the groups providing an ideal environment for the galaxy interaction and mergers. And just let me to stop sharing. Okay, it's maybe better. The galaxy mergers, and we try to understanding what is the impact of mergers and the interaction of galaxies into the kinematic properties of galaxies. And you can see a typical merger of the galaxies in the galaxy groups and clusters. There's and the impact of merger on the galaxy may differ depending on the type of mergers. Minor mergers are less disruptive, but more frequent, while a major merger can significantly transform a galaxy's morphology and dynamics, which here we focus on the dynamics of galaxies to see how it's changed during the merger history. And the merger also means that the secondary galaxies bring new gas or dry, and which means that the merger does not bring new gas, and we should divide it to the gas-rich and gas-poor mergers. And also we have stellar mass functions. Here it is the shape of stellar mass functions can be explained by merger and star-forming galaxies process. You can see in the shape of a stellar mass function in the bottom panel of figures, there's from Raouf in 2016 that's characterizing the galaxies into the spheroid and disk galaxies. Says here that's showed for all galaxies, you can see the trend of Schechter functions for the mass function of galaxies, and while you divided the galaxies into the spheroid and disk galaxies, you can find some difference into the statistics into the statistics of low mass galaxies and high mass galaxies, which it seems that in the high mass galaxies the mergers draws the galaxies to the most massive galaxies which we have in the world and in the universe, and instead we have the lower statistics in the low mass galaxies, which means that this type of satellite galaxies may merge into their group central or other satellites. And for the star-forming gross galaxies, we have still high fractions of the galaxies that didn't merge to the big galaxies or the same mass galaxies or satellites. So, the galaxy kinematics, which able to measure of the motion of the luminous gas and stars using the integral field spectroscopy, we provide fundamental tools for answering basic question about when and how these galaxies formed. So you can see some of the example of our samples to the figures, the stellar and gas kinematics, along with the optical image of the galaxies. We have in our sample. This is 3 samples from the SAMI galaxies. You can see in the map of size, stellar mass. Lots of which is introduced by the Capillary in 2012. Lots of galaxy types there. You can see the different type of galaxy size into the stellar mass, and which is divided to the fast and the slow rotator or galaxies. What we focus on here in these studies is the early type galaxies, which divide into the fast and slow rotators, which is mostly fast rotator BGGs. And you can see, I can show this categories of the galaxies by the red line into the map here. So okay, let me show some of the impact of mergers on the gas disk of galaxies. This is the cosmological simulation by Van der Waals in 2015 show what's impact of mergers on the galaxy and the gas particles. You can see the contours as a star particles and the star, and also you can see the color particles as the star particles. So from the first panel show the gas disks before the merger, and the second panel this is right after the merger when most of the gas disks has been destroyed. So the galaxy formed a misaligned gas disk through the accretion, as can be seen in the third panel. And the gas disk is seen to rotate in the first panel due to the continued misaligned gas accretion. And at the late time, it is a bit warp, clearly visible in the fifth panel because the gas disk torques with the stars, and the stellar torques are stronger in the center, which therefore realign first. So the last panel showed that the gas disk is almost completely aligned with the stars. So you can see these formations and this impact of mergers into the gas particle of disk. And so the misalignment persists for, it seems that roughly speaking, the misalignment persists for about 2 gigayears before the gas star misaligned angle drops. Such a scenario is lead us to make motivations about for studies that some of the previous studies in which some of the previous studies show that the mergers highly impact on the gas dynamics compared to the stellar dynamics. And I said that in the previous slide, there is an offset 2 gigayears during the re-accretion of the cold gas, especially for the elliptic galaxies. And there's lots of source of halo, source of gas accretion is external and internal source of gas accretion, which lead to have a misaligning position angle offset between the gas and star rotation axis. The external source of gas is coming from the filament accretion, and this is based on some studies in cosmological simulation, March 2015, which is called gas accretion from the filament, and the internal gas accretion may be coming from the galaxy interaction, galaxy-galaxy interaction and gas-rich mergers, which is happening into the galaxy groups and clusters. And we have some evidence to show the external dust impact, the external dust that's coming from the mergers impact on the stellar gas misalignments. Such impact is higher than producing the dust with the BGG stars. And finally, we try to understanding what's happening for the relaxed systems, which have a lack of recent major mergers during several gigayears ago. There's some publication showed by this started with Pohlmann in 1994 that introduced a class of galaxy groups which is located at the final evolutionary states of and this people and lots of publications coming working on such galaxy groups which named as a fossil galaxy groups. Such a galaxy groups is defined based on the large gap between the two most brightest galaxies, which are producing based on the dynamical friction and the merger of satellite galaxies to the galaxy center in the earlier time of the universe, and also have a higher X-ray luminosity, which unaffected by the mergers. So this motivation is lead us to identifying the relaxed galaxy groups first, and then try to comparing the central galaxies, which is located in this is hosted by this type of systems with the unrelaxed galaxy groups. So let me to have a brief introductions of identification of the relaxed and unrelaxed galaxy groups using an optically measurable parameters. There's to understanding the galaxy evolution. So we have two different optically measurable parameters: the luminosity gap between the first and second brightest galaxies that I mentioned in the previous slide, which is using as a conventional definition for the fossil galaxy groups. And another parameters that we added in 2014. This is the offset between the central galaxies or BGGs and the luminosity weight of galaxies, which some studies showed these parameters is really important to show the relaxedness state of the galaxy groups, and where the BGG are more deviated from the luminosity weight of center of galaxies. It seems that the groups are more unrelaxed compared to the groups in which the BGG is exactly located at the center of luminosity weight. So this you can see the regions of red and blue as the relaxed and unrelaxed galaxy groups, and typical sample of gamma observations. This is the post stamp image of the relaxed and unrelaxed samples. You can see this the unrelaxed systems are more crowded, and the relaxed systems have a really big elliptical galaxy at the center with some small satellites. So such a motivation is lead us to trace back the evolution of these two types of systems into the cosmological simulation, and We can see the relaxed systems accumulated more fraction of their mass at the earlier redshift range, and while the unrelaxed systems didn't form at redshift 1 if we considering the formations of the galaxies is more than 50% based on the algorithm. And here we're using the merger tree of the Millennium simulations to trace back the evolution. And we showed that the relaxed systems are completely early formed galaxies based on such a definition, and the unrelaxed systems are late formed galaxy groups. And you can see the substructures of the relaxed and unrelaxed galaxy groups into two figures that, sorry, my slides didn't change. I think okay. Sorry, can you hear me? Was it just
yes.
Get it back?
Yes,
okay.
You very well. Yeah, you are now the motivations. I mean, slides start with motivation.
Okay. My slides changed, but I think it didn't change my slide. Just talking about the motivation of the studies, is, which we see that the impact of the mergers on the gas dynamics is larger compared to the stellar dynamics based on some previous studies. And as I mentioned, that there's some evidence for the external and internal source of gas accretion, and which such a gas accretion can lead to have a star gas misalignment angle, which lead to persisting the misalignment, say to the 2 gigayears during the accretion of after the accretion of the cold gas, new cold gas, based on the Van der Waals in 2015. And so we have the relaxed systems too. Okay, just let's see the next slide. This is just really slow. So we try to identify the relaxed and non-relaxed galaxy groups, which based on two different observational measure parameter is the luminosity gap between the two most brightest galaxies and the offset between the luminosity centroid that I defined it before. And you can see the regions of blue and red for a typical galaxy, central galaxy which is hosted by the relaxed and unrelaxed galaxy systems, and which you can see the unrelaxed systems are more crowded systems, while the relaxed systems have a really bright BGGs at the center of galaxies. So to expect the evolution of the relaxed and non-relaxed galaxy groups into the cosmological simulation showed that such a relaxed group has accumulated more fraction of their mass, more than 50% at the redshift, at the higher redshift. This is the redshift 1, and while the unrelaxed systems didn't form at redshift 1, and is just less than 30%. And if the formations definition of the galaxy is the 15% of the final halo mass was. And you can see the substructures of the relaxed and unrelaxed systems, which the relaxed systems are completely early formed based on the cosmological simulation definition of these systems, and unrelaxed are late formed. You can see more substructures in the relaxed systems compared to the unrelaxed one. So here, okay. We investigate on the major history of these two type of galaxy systems in order to understanding the merger rate and the time-to-mass major version of the central galaxies on these two type of systems. You can see there is a difference in the peak of a merger rate in two different galaxy groups, into the central galaxies of these two different galaxy groups. And you can see here the peak of relaxed system, peak of a merger rate for the BG of relaxed systems are earlier compared to the unrelaxed groups around 2 gigayears. That's the time we need for persisting of the misalignments between the gas and the stars. And also, we have a higher fraction of recent major mergers, less than your major mergers for the unrelaxed BGG compared to the relaxed one. So such a motivation lead us to identifying these galaxies into the gamma and semi survey. The reasons that we're using the gamma in these studies is which is in this survey is more deeper than SDSS, and we can estimating more probable relaxed systems based on the higher gap parameters in which you can see in the inset figures as R mag versus the delta gap, delta magnitude. You can see is this brightest galaxies instead of the and comparable compared to the second brightest galaxies, which is in the gamma galaxies is more completed than the SDSS. Yes, to estimating the magnitude gap between the two most brightest galaxies is go to up to 2.5 wide, and compared to the SDSS, that's is stop at 2.5 due to the completeness of redshift and the magnitude of the survey. So you can see the regions of the stellar mass and redshift distribution of gamma galaxies, and which is semi is bolded by the red line. So in order to understanding the age and activity, stellar population properties, and the kinematics of galaxies, that's I just focus on the kinematics of galaxies, which is more relevant to the topic of the context of this workshop. So let's start with the stellar population properties. We show in the map of gap and offset parameters, and just if you remember the regions for the relaxed and unrelaxed systems in the 1 and 6, you can see we have more red pie to the pie charts are compared to the regions. The panel of 6 is we have the more blue regions. What is the blue and red? Is the blue is the active and passive galaxies respectively, blue and red. This is based on the NUV minus R colors. And you can see we have more fraction of the relaxed systems are active galaxies. This is more blue. Sorry, this is passive galaxies is more red, and compared to the more high fraction of blue galaxies in the unrelaxed systems. So we know that these parameters is sensitive. This is not independent of the morphology and also the dust mass of this type of systems. So you can see in the left panels that we have the NU minus R colors versus the specific dust mass and Ceaseless index, and you can see we have still higher NU minus R color, and Smith-Nathan higher means the redder specific NU minus R colors at the fixed dust specific dust mass, and also at the fixed Ceaseless index. So we also check the metallicity and the star formation rate of these two types of systems, and you can see we have a higher metallicity in the BGG of unrelaxed systems, which is maybe back to their massive building blocks of this galaxy systems, and which is over the median of all samples, and we have the lowest star metallicity for the BGG of the relaxed systems, which have a lack of recent major mergers, and the merger rates have a 2 gigayear different in the peak. And also, we have a higher star formation for the massive galaxies, which is located in the unrelaxed systems compared to the relaxed one. And this is higher than the median of the median trend of the total galaxies in the sample. And this is maybe back to some of the disky-shaped galaxies which is available in or sampled, or maybe due to the number of mergers that's happening for such a galaxy groups. So let's start with the impact of dynamical states on the stellar kinematics of galaxies. We try to have a Fourier analysis on the structural velocity field, which leads to estimate the kinematic asymmetry for each galaxy. What's the kinematic asymmetry? The kinematic asymmetry is the fraction of first and ones order of magnitude or the amplitude of the Fourier harmonics on the velocity data. So you can see the image of a typical really ideal regular, and we just to say that we intend to mark galaxies as a regular and non-regular rotator hosted by different dynamical halo states, and you can see the regular and quasi-regular and non-regular rotators is really ideal cartoons, which you can see the criteria for such fractions, which the K1 means exactly the rotational velocity, and the K5 is some of the kinematic anomalies in that. So you can see a typical example of the regular, quasi-regular, and non-regular in our sample that we can identify into the different dynamical halo state. So let's see the chart in the top panel. You can see, let's see the histogram in the top panel. We can dividing the regions of the regular and quasi-regular and non-regular rotator BGGs. You can see there is a strong peak for the regular rotators belong to the BGG located hosted by the relaxed systems, and this is drop in the higher kinematic asymmetry. And we have while we have a stronger peak in the quasi-regular and the non-regular for the unrelaxed BGGs. So let's investigating on the kinematic asymmetry in different stellar mass range. You can see the trend is trend of kinematic asymmetries grows with the stellar mass increasing the stellar mass, which is showed by the gray line for all sample. But individually. We try to understand. We try to focus on the regions that we have a significance in the statistics, which showed by the gray. Here, this is just to testing what's the impact of statistics in our analysis. You can see around 83% of the galaxies, which is located in the beams of 10.8 and to the 11, have the regular rotators for the relaxed systems, while the unrelaxed systems spread over the wide range of the kinematic asymmetry and spread with the same fractions in there. And you can see also higher fraction of the BGG located in the unrelaxed systems are more non-regular in the next beams. This is the 11 to 11.12. So here you can see some of the impact of the dynamical halo states on the kinematic asymmetry of the BGGs to see whether there's any impact of the mergers on the kinematic asymmetry for such a galaxies. So in the case of rotational classification in the stellar kinematics, we try to show the conventional diagram for dislocating galaxies into the slow and fast rotating BGGs following the study of M. Sulim in 2012 and in 2016. Then try to understanding the spin electricity relations, which the spin is using as a proxy for the angular momentum of galaxies. Here you can see the map of popularity in 2016 for the different categories of galaxies. These spiral, S0 galaxies, and elliptical galaxies regions. We just focus on the early type systems. You can see in the map of spin ellipticity relation, which we estimated into the effective radius, which we can clearly see in the bar chart. In the bar chart, the fast and the slow rotators BGG based on two different methods. It's just clear to see that we have the most fraction of our galaxies in this study is fast rotating BGGs, which you can see a sample of fast rotator BGGs is here in the left panel, and some of the fraction of the such a subsamples is the slow rotator BGGs, which we have a higher fraction of slow rotator BGGs in the relaxed galaxies. So let's start with what is the impact of dynamical state on the both star and gas kinematics of galaxies. You can see the map of magnitude gap between two most brightest galaxies and the offset parameter that I introduced previously to the regions of the two regions of the blue and the red. You can see the pie chart and the red regions in each pie chart. You can see we have more red regions in the pie chart of relaxed and unrelaxed compared to the unrelaxed systems. What is the red? And the red is the alignments star and gas galaxies, which you can see the example of in the top panel, stellar SK and GK, which means that SK means the stellar kinematics and GK means gas kinematics. You can see there is the gas follow the stars in the alignment galaxies, which I showed the definitions in the next slide of the alignment, misalignment, and counter-rotating galaxies. And we have the blue regions in the pie chart. You can see the higher blue regions in the unrelaxed systems. It means that we have a higher misalignment and between the gas and the stars in the unrelaxed systems. Then you can see the misalignment into the you can find the misaligned regions into the panel that I showed to you here. This is you can see that the gas doesn't follow the stars, and you can see there's a misalignment between the position angle, which I showed by the dash line here, and also some of our galaxies consisting of the misalignment. This is just labeled as a counter-rotating galaxies, which you can see here. We have some of our fractions. This is not it is comparable to the relaxed and unrelaxed systems for the counter-rotating galaxies, which means that this is exactly we have more than 150 degrees difference into the alignment of the galaxies, and the gas doesn't follow the stars. So, and you can see this just back to the different substructures of the relaxed and unrelaxed systems. And we have also the black regions is just the low signal to noise galaxies, which in order to selecting the just early type galaxies in our samples, in some of which the galaxies have a really low star formation, and the H alpha signal to noise is really low in this case, and we cannot trust to the fit of the gas kinematics or this type of galaxies says to decide this is aligned or misaligned galaxies. And around 20% of our samples is the low signal to noise galaxies, which we just reported here, and I can explain it into my future slide.
Mojtaba, just you have like 1 minute left.
Okay. This is just to confining the previous slide. I just have a gas slow misalignment distribution for the two subsamples. As you can see, we have the strong peak for the alignment C of the relaxed systems, and where the misalignments where the unrelaxed systems spread over the wide range of misalignment angle between the gas and stars. And you can see the same regions for the stellar mass dependency of the misalignment angles. You can see in the regions that we have more reasonable statistics to comparisons. We have the more than 62% of the galaxies just hosted by the unrelaxed systems are aligned, and compared to the less than misaligned, less than alignment C for the unrelaxed BGGs. And we find there is a stronger correlation between the misalignment angle and the stellar mass in our subsample because of we focus on the galaxies which is located in the galaxy groups, the brightest galaxy groups compared to the stereoscopic index. And you can see in all samples or a strong correlation with the stereoscopic index considering the misalignment angle versus the angles using the linear correlation function, and you can see in the regions of the stereoscopic index we have also a high fraction of galaxies located in BGGs located in the relaxed systems are aligned. So just to show some of just to show this is really low to loading. So just can't see the slide here.
Mojtaba, shall we stop here and then go to the questions?
So I think the slide is not loaded. I think this should be stopped. I guess this is just the last slide. I think. I don't know. So I can't see the slide.
Okay, we can start with questions, and then if it's loaded, then you can briefly go through it.
Okay. Just I try to show some of the examples of our high signal to noise galaxies with doing some analysis on the convolution of the expaxels using the Gaussian kernel, and then just try to show some analysis on the lowest star forming galaxies based on the machine learning algorithm. But the final talk is exactly this is a summary of just to summarize the main point of my talk is we try to using the gamma and semi observations to demonstrating the difference between the gas stars, position angle offset for the BGGs, which is located in different relaxed states of the galaxy groups, and which show that the relaxed groups frequently have a lower gas star misalignment angle compared to the unrelaxed systems. Which is have a more experience in gas which measures previously, and we show some of the impact of such a dynamical halo state on the stellar kinematics by Fourier analysis on the structure or rotation of galaxies velocity field, and we showed that the BGGs in relaxed groups have a lack of recent major, lack of recent major mergers, and created the new gas really early time of the universe, the misalignment, rotation axis and stars. This is the and we found the stellar metallicity and the star formation rates, dust, and any monostar color are different in the BGG relaxation systems, and they finally showed that the luminosity gap parameter is the important is driving parameters for this entangle between these two type of galaxy systems. Thank you.